So Friday afternoon. I need to find a room, which is, I guess, is the most difficult part of that. And on the Friday afternoon, so that would be a makeup lecture. And what we actually need in that makeup lecture is that please bring your laptop. We will have another programming sections to see whether we can put the consolidations problem there in Phoenix, okay, or in other code of your choice. And also we can have using that time slot to also discuss the final project. I will try to utilize that time to meet with individual every single one of you. I will see whether I can find the room. If I can find a room, that would be, I'm hoping that would be around 2 to 4 p.m. Is that okay? If not, I will try to find the time slot at 3 to 5 p.m. I'll try to confirm it today, okay? So last time we talked about the pole mechanics problem. Basically, we have that K, B, T, B. We have these formulations. Okay, so this is actually the linear system of equations. And this is actually after we time discretizing the time, okay? So without the time, we will have extra term on the weight dependence, and then that term would also include some term from the previous time step. Okay, so now this time, what I actually want to do is to focus on a more generic problem. If I have this matrix system, and that actually show up a lot mathematically in a lot of deviations. Maybe F. Okay, so consider this generic system. How do I solving it? Okay, so in your undergraduate course or in your final element course, most of the problem are single variable boundary value problem. So what you want to solve is AX equals to B after you linearize, okay? Even though you have a nonlinear mechanics, if you're linearizing it incrementally, you actually need this linear solver, okay? Just to refresh the memory a little bit. So that linear solver, how do we actually solving this linear solver? Okay, we just put it in MATLAB and then inverse. Okay, but MATLAB probably do something, right? So what did MATLAB do? Yeah, LU decomposition is one way. Now there is also iterative solver that doesn't really exactly decomposing it into LU, but you're absolutely right, there's one way. Now, I guess to think about these questions, we also need to think about what make it easier to solve. Okay, so and then what makes it easy to solve? Okay, so what make it easier to find X? Okay, it's a very simple questions. So does that depend on the property of B? They more or less depends on the property of A, right? Because we all know if A inverse exists, right? So if A inverse exists, then AX equals to B simply imply A minus 1 AX equals to A minus 1 B, right? Okay, does that make sense? Okay, does that make sense? Okay, so now let's go back to these questions. Let's think about it deeper. what make A minus 1 exist? Okay, what make A minus 1 doesn't exist? Okay, is to have a singular square matrix, right? If you have a square matrix that have eigenvalue equal to 0, okay, the inverse doesn't exist. By the way, does that imply that you cannot solve the problem? Actually, you can still solve the problem. It's just that you may have X will not be unique, right? Okay, you will be finding a subspace of that X, okay? So let me give you an example. So it could be possible that there is no solutions, but it's also possible that you can find non-unique solutions, right? Let's say 1, 0, 0, 0. Okay, this is the simplest A matrix, okay? Is it positive definite? It's definitely not positively definite. Okay. Okay, do you have a solutions? Do you have a solutions? Actually, you do. X equals to 1. Okay, what do you know anything about Y? You don't know anything about Y. In fact, any Y will fulfill that solutions, right? Even you put a complex number there on Y, it will still be okay, right? Okay, so what actually happened is that singularity itself doesn't imply there is no solutions, but singularity guarantee that you don't have unique solutions, okay? Or on the other hand, you can also have something that have no solutions, okay? Just contradict to each other. The first equation and second equations, they cannot simultaneously exist, okay? So let's give another example, 1, 2, 1, 3. Okay, so what happened to this? Okay, basically there's two equations that actually contradict to each other, right? You see what I mean? Do you think you can solve an equation there? Actually, maybe you could. So maybe let me put another thing that are actually a bit more guaranteed to fail. Okay, something like that. Then you may actually have problem. Now, this is actually for a single variable solution. So if you solve KU equals to F, do you remember where you see these equations? You see that in your truss analysis or matrix structural analysis, or if you solve a Poisson problem, you will have that, okay? So I will say the following. In general, for single variable problem, you want this to be positive definite. Okay, so, and what does that mean? Okay, so what is the difference between positive definite and invertible? Are they identical concept? Okay, what is the requirement for a matrix being invertible? Yes. Yeah. So what is the eigenvalues of that matrix that are being invertible? Huh? It's full rank. Okay, this is actually a beautiful answer. What does it mean by having full rank is that all the eigenvalues are non-zero. It could be negative, by the way. Okay, you can still have row space that are independent to each other, or column space that are independent to each other, even though the eigenvalue is negative. Okay, but positive definite give you one very good property in the sense that if you consider this system. Okay, what is this? This is usually energy, okay? This is actually called quadratic form, okay? So if K is actually positive and symmetric, then what happened to E? E would be non-negative, okay? It could be 0, okay? But it would not become negative, okay? So in a lot of mechanical system, you want to come up with a positive definite matrix. And also another issue of this is that if this is not symmetric, you have a skew symmetric part, and what happens when you compute the quadratic form of the skew symmetric part? Okay, so let me put the example. 0, 0, minus 1, 1. Okay, this is skew symmetric. Okay, if you put a vector here, you put a vector here, what happens? Okay, they would cancel each other. Okay, so you end up, that doesn't really count, but then so your energy and your first derivative doesn't corresponding to each other, and you actually lost the ability to write the system in a according to the variational principle. Okay, so here in this lecture, I want to talk about two aspects, and they're very related. The first one is the variational calculus. Which actually allow us to derive the governing equations without finding the strong form and put a wave residual there. And then the second one is actually the stability from mathematics analysis. Okay, we want to look into the matrix, okay, and then we want to talk a little bit about the analysis to guarantee the unique solutions, okay, of the mixed system, okay. Now the challenge of the mixed system is that you actually have this broad matrix. Okay, so and oftentimes this part is 0. Okay, so this is good that at least one of us actually know the column space has to be independent. This is already very helpful. Okay. So, but one thing that I actually remember is that this B term, coupling term, they are not square matrix, they're rectangular matrix. Okay, and this is actually square. Okay, and then actually when you compute the whole system, if you assemble the system of equations, you will find that you would actually have an eigenvalue that are of very different magnitude. So, and you actually need to able to solve the block system by actually ensure the stability both on the A and also on the B term. So the fundamental question is that how to find or derive the right coupling term. Okay, how do we make this thing stable? Okay, it's a rectangular matrix. Okay, now, but then the first thing to remember is that you always need to have enough rank. If you lose the rank, it's game over. Okay, does that make sense? If you lose rank, you guarantee to have singularity, but later on you will find that having enough rank is actually necessary but not sufficient to guarantee stability. Okay, and then we will explain why in the next lecture. So let's first talk about the variational calculus. I want to point out the difference between the pole mechanics and all the other problems that are coming from a constraint optimization problem. Okay. So anyone know what is the optimization problem? Okay, optimization problem is that I have loss functions, and then I actually try to find a minimizer. Okay, I think everyone in machine learning know. So here, what is the, or how do we actually get the governing equations? One way to think about this is the following. We can actually recast our problem as in the variational versus the variational principle. And how we're actually going to do that is that we actually simply find the energy function or that take the first derivative, or will give us the governing equation. So let me talk about that. So this in mechanics world is actually called either Lagrangian mechanics or Hamiltonian mechanics, depends on how you frame the problem. Okay, so and from the a field of linear programming, we can also call it, or optimizations, we can call it constraint optimization problem. So let's consider the undergraduate problem, KD equals to F, okay? Now, consider a system that looks like this. Just to give a picture. Okay, I'm putting the material, and then this is actually fixed. Okay, is it easy to understand? And I put 4 degree of freedom here, which is 6 degree of freedom, and I build some truss. Okay. Now, this is actually not necessarily having any constraint, but here I want to say the following. I actually introduce a reinforcement learning there, okay? Now, so that, or maybe I put a spring there, so that I would have a constraint that if this one move D, this one would move half of D, for example, okay? So that would be an additional constraint. I want to put it into the system, okay? So that system would actually affect how much energy it stores and need to taking into account, for example. So if you can actually write the constraint here, so that would actually introduce the constraint to the system, and then we would say that it's actually subject to dq equals to g. Okay, I'm simply controlling a subset of the displacement degree of freedom to actually obey a certain constraint G, right? Okay, for example, let's say call this node 1 and call this node 2. I want D1 equals to 1/2 of D2, and then the constraint that I want to write, let's write, so you see to write constraint, D1, D2 would be D1 minus 1/2 D2, okay, equal to 0. Okay, does that make sense? Okay, so, and it doesn't need to be equal to 0, it could equal to 5, but then you will always, but you can actually minus both sides by minus 5, and then you get the equation something equal to 0. Okay? Now, what is the difference between solving this problem? Okay, to answer that, then we actually need to think about how to formulating the particular problem. Okay, so in this particular case, I need to think about how to write this constraint. Okay, and then let me write this as something like this. Okay, so this is actually a very simple row function vector. 0, 0, 0, blah, 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 1, 0, 0, 0. Okay, so at the Q row where I want to put additional control, I simply put 1 into the into the constraint. Okay, does that make sense? Okay, so for example, I want to control the first 2 nodes, then that would be 1, 1, 0, 0, 0, and then okay, etc., etc. Okay, so Q is not necessarily just 1 node, but it could be multiple nodes. Whenever you want to put a constraint that are actually coupled, you just indicate that is actually 1, or you could have 2 constraints. Okay, each constraint actually only control 1 degree of freedom. In fact, it's actually perfectly fine and in finite element, or in particular in explicit scheme, a lot of time people use this technique, writing the constraint instead of partitioning the effective stiffness matrix to enforce the essential boundary conditions. This is very common in production code. Okay, for better balancing or for whatever reason, for domain decompositions, you also need that putting this constraint. Do you guys know what is a domain decompositions? Okay, you're a big file element mesh. You actually doesn't want to solving it in one computer, and then you cut it into multiple bases, a subdomain. But this still require communication, right? And then you can use Lagrange multiplier or penalty method to actually introducing this. Now, let me formulate the problem in in a Hamiltonian, in a variational form. In this case, the problem would be the following. I want to minimize the following thing. This is a scalar functions that take d as a vector, and that I write 1/2 dtk dt minus f. Okay, so the original governing equation is kd equals to f. Okay, K is a matrix and is symmetric. Okay, and this is actually called functional. Okay, it's not a functions, but a functional. So, and what it actually implies is that you are, if you say something is the energy functional, underlying it, if you take the first variations, you will get something called Euler-Lagrange equations. Now, I'll subject it to constraint, and then the constraint could be GD equals to, let's just put 1 degree of freedom, okay? I just want one particular component of D equals to G. Okay, so that would be the originally constraint optimization problem. So when I say minimize, what I mean is that find D such that FD become smallest. Oh, sorry, maybe minimize, not necessarily smallest, it could be negative. Okay, does that make sense? Okay, so this is the original constraint optimization. This is the original constraint optimization problem. If you want to solve PIN, basically you can just try to minimizing this energy functional subject to this constraint. Okay, you can also solve the PIN that way. And then if you find the D is actually the entire solution field, you can find the solutions. Okay. Now the problem is that how do I enforce this constraint? Okay, let's visualizing it a little bit. If I write the energy functional, it could be in some parametric domain. Let's say I only have 1 degree of freedom, and then I basically have D, and then I have the function F, and then I will do this. Okay, so this is the minimizer at the minimum, right? You see what I mean? There's no point lower that make F smaller. So this is actually my minimizer. Does that make sense? Now I put a constraint there. I say that F or D actually have to be greater than 5 or whatever, okay? Or actually maybe in this case actually under constraint. But let's say D, let's put the constraint that D must be equal to F, okay? Maybe it doesn't make sense, I'm just making it up, okay? So what would happen? So what is the new minimizer? Okay, so I have to draw a straight line that 45 degrees, right? Okay, and then this portion is not valid because in these portions, D is not equal to F, okay? Only in this line. So I only basically have these 2 points, right? Okay, so now I have a different minimizer because of the constraint, which makes sense, right? You solve something and then there's a constraint applied and then you may have a new minimizer. The issue is that how to formulating it how to formulate it or amend that equations. And I think that we all learned that, how many of you heard of Lagrange multiplier before? Okay, I'll go over that quickly. If not, that is actually fine. Now the trick to put the constraint is actually to actually change the energy functional by actually write a new energy functional that enforcing this to be valid, okay? Now, that comes with the price, because in order to enforcing that, I need to introduce extra degree of freedom. Does that make sense? Like in mechanics, we see it a lot, incompressible Navier-Stokes equations. Okay, how do I enforce incompressible constraint? I can actually recasting it as a Lagrange multiplier approach, and what I need to do is the following. I will define something called, in this case, a Hamiltonian. Actually, you can also call it Lagrangian. We are not solving any dynamic problem. Okay, a Hamiltonian actually is a specific energy functional that yield the Euler, that yield the governing equations. Let me call this thing M. I write the new energy functional that actually have the original unconstrained energy functional part, just the elastic energy, and I would actually add M GD. Okay, M is actually unknown. We don't know what it is. It's actually called the Lagrange multiplier. And it actually, in this particular case, F is actually the energy. Okay, and actually M times the constraint also give us another energy. Okay, the M and the GD is actually conjugate to each other. Okay, so, and then I would actually come up with a new energy functional that both depends on the displacement in the previous example, and also the Lagrange multiplier as the unknown. Okay, so actually, how do I find the governing equations? In this case, the governing equations would be the first derivative of respect to d, or the s, not or, and the first derivative of the Hamiltonian with respect to the Lagrange multiplier. Okay, so let me look at it in a particular details. Okay, so Fd is actually equals to 1/2 the quadratic form of that store the elastic energy, the external work coming from the work done from the external force, and then the extra term is actually this. Okay, so as you can see, this is always 0. So in terms of the magnitude, F is actually not changing because this term is always 0, isn't it? Okay, but we are not actually interested in the values of H. We are interested in the first derivative, okay, which is actually the tangent of H with respect to D and M. So if I write the entire H would be equals to 1/2 dt kd. Sorry, I think this one underneath the transpose. Kdf plus M Okay, so far so good. Okay, so far so good. Okay, now I take the first derivative. Okay, what is this first term? Okay, so I'll take the derivative of dt and then take the derivative on d, but recognizing that k is symmetric, so I can swap it, right? So if I actually put the two terms together, I have 1/2 kd and 1/2 kd. Both of them give me a vector, okay? And then I combine it together, I basically get AD, right? Okay, so the second term is just F, okay? So I get back the original one. Now I have the new extra term that actually doesn't appear before, so what would that be? So G is a constant. So G, take the derivative of, so the G corresponding to D will be cancelled out because G is a constant, right? It's not depends on D. So this is equal to 0. And this one, D, the derivative of D with respect to D is, of course, just identity. So what we end up is that we will have that extra term, m equal to 0. Okay, just swap the order because of the IT term. Okay, so how about the second term? The second term, we don't actually, in the derivative with respect to the Lagrange multiplier, we don't care about this because none of that actually depends on m, right? Okay, so the only thing that we care is the original multiplier, original constraint that we put in there. Okay, so we do a lot, but then the second equation just get back on what we it's just a constraint, get it rewritten. So what you actually need to pay attention is not the constraint you put in, because you always just put this equation in the second column or whatever, but this additional term that you add in the first equations to fulfill the constraint that actually change the minimizer positions. So if you look at this system, this is actually the simplest, one of the simplest setup of the mixed system that gives rise in the lots of problem, including incompressible flow, including incompressible elasticity, is actually something that take this form. Okay, does that make sense? Now, these two set of equations is actually called the Euler-Lagrange equations. Okay, does that make sense? Okay, it's simply implying that the governing equation that you put in there is coming from an energy functional, which is a scalar. Okay, so the formalism of Hamiltonian mechanics is very popular because you think about that. If I can find one expression of the Hamiltonian, then I unlock the secret of the mechanics by solving the Hamiltonian optimization problem. I just need to optimizing it, and then I will have a very complex way to represent a system. If you take a physics class, the Hamiltonian use a lot to represent a pendulum or very complex structure. Usually in the physics class, you only have 1 or 2 degrees of freedom just to elucidate the idea. But there is no limitation on that. In fact, you can write a Hamiltonian with thousands of unknowns. This D would simply be all the unknown of your final element. Okay, you see what I mean? And again, if you solve the PIN physics informed neural network, you simply need to minimizing this directly with D and the Lagrange multiplier. Now, but what is the practical difficulty is that in here, this I have very simple property because it's simply a rectangular matrix with everything 0 except one column. Okay, and you can easily check whether I have enough rank that are given to it, right? Okay, but we actually don't know whether the problem is solvable. Okay, when a system have no unique solutions, it may not be, you may not even able to find the solution space. Okay, when the solution is unique, you have a unique combination of D and M that actually fulfill the governing equations. If the equation is not unique, you have a space of equations because there are multiple solutions that can fulfilling that, and that actually introduces a space of your solutions. Okay, so there are two issues. By the way, there is more details to it. This is actually the Euler-Lagrange equation is not the first variations of it. Do you guys know the difference between the two? Okay, let me do it. Let me do it slowly. Okay, if you actually want to compute the first variations, which would directly give you the weak form but not the strong form, okay, in a finite element, this is what you should do. let's put it into details. Okay, let me actually write a homogeneous system just to make it slower. Let's say this is actually the system I have, and I want to compute the first variations. Okay, I write it something like this, and what I'm going to do is that I'm going to write dt, and I'm going to put a variation there, and then I'm going to put the term alpha there, and I'm going to put k dtk alpha delta. Let me put the same color to make it more. Let me use the same color to make it look nicer. Oh, still wrong. Okay, so is it the case? Yeah, so to compute the first variations, I need to do the following. I will take the derivative with respect to alpha, and I'm going to push that alpha equal to 0. Okay, does that make sense? Okay, the previous one, I directly take the derivative with respect to d, right? I take the derivative directly with respect to h. Now here I do something slightly different. I take the derivative with respect to a scalar, the perturbations, along with a certain directions, delta d, and I'm going to push that d as small as possible until it becomes 0. Okay, you see what I mean? So what would you get there? You will get a different form. What you would get is that you will get this. Okay, sorry. I think I'm making a mistake. There's no T here. Okay. I don't know why I carry this up. Okay, does that make sense? You can try it. Let me do it in details. So let me. Oh, what happened to this? Okay. So if you actually, let me also clean up this. Okay, so I would actually just do the integration by part. The first part I have is that I would simply have this 1/2 k kd plus lambda delta t alpha equal to 0. And then the second term I will have is 1/2 kd alpha dt k okay, do you both agree? Yeah, simply have two terms. One take the first derivative and other take the second one. Okay, you see what I mean? So here, do you know why I get this term? Because the first thing is there is no delta here, right? There is no alpha here, right? So when I take the derivative, it becomes 0. Only these terms are right, and I just take this thing out, so I get this term. Okay. So let me work out this. So I apply this to d. Okay, d is actually not is independent of alpha. So dt d alpha equal to 0. And this one, I have the alpha there, so I simply, the alpha, the derivative of itself is actually just 1. So I take this thing out, and then alpha equal to 0. So, and then because alpha equal to 0, this term also cancel out, this term also cancel out, so I end up with simply this. With dk. Okay, and then because k is symmetric, so I actually combine them together. I will take out the 1/2, and I end up with just this term. Okay, does that make sense? Okay, why do we care about this is that this can also give you the width form, because if you think about it, if I add the additional term there, then the first variations respect to D would be actually equals to would be simply equal to this. Okay, what is this? If I actually put the final element discretization on D and put this as the variations, I will get back the weak form. Okay, does that make sense? Do you guys get the idea? The only difference is that I no longer need to have a strong form and put a weight there and then deriving the governing equations. I will start with an energy functional. And why we are interested in that is that sometimes it's good to know what is the property of H to indirectly control the tangent. If I know H is stable, I know that my governing equations along the D or whatever D is going to be stable. Okay, so it's just another way to think about the same problem or another formulas that are actually of practical values. Okay, so now is that the only way to do it? Actually, there are two more ways to actually enforce the constraint. Okay, one is a penalty. Sorry, we cover the Lagrange multiplier. Another one is a penalty. What is the last one? I just do both. Okay, it's actually also possible, and I can explain. Let me quickly go for the penalty. Okay, penalty is actually alternative where we actually don't want to explicitly enforce a constraint, we only want to approximating it. Okay, in some sense, it's also kind of similar to PIN, where we have multi-objective and we don't want to introduce a Lagrange multiplier. So is a Lagrange is actually a approximate approach, and it has its own benefit in the sense that you don't actually introduce extra degree of freedom. I will go for it very quickly. Instead of introduce M as an independent degree of freedom, I was simply saying that M is actually K times the constraint. Okay, does that make sense? Okay, what am I doing here is the following. Okay, so I want to actually modifying the energy so that whenever G is not fulfilling, whenever the constraint is not fulfilling, it's going to introduce a penalized energy. Okay, then make it not the, or then make it far away from the minimizer. Okay, does that make sense? Remember, the original goal is to minimizing the energy functional, right? Okay, but if I put this term there, then if K is very large, this is also another trick. If K is very large, okay, I would be very far away from I would actually prevent my solution for making this constraint getting violated, right? You see what I mean? Because my original goal is minimizing the energy functional. But now, if I actually violating that, it would the loss function or whatever we're going to shut up. So I will not minimizing that. I will avoid this point. Okay, so to write that is actually very simple. I just actually put this, and then I just introduce a new energy. Maybe I will call it P. It's actually simply M times that constraint. Okay, you see what I mean? So that would introduce the energy and put it on top of my original energy. Okay, so I will simply write this as the original elastic energy plus work done times that penalty energy. I just put a minor there I just put a 1/2 there just to make it quadratic. But actually you can take out the 1/2. Do you know why? Because K is a parameter that you actually don't know how to, you actually just know that it's very large. You see what I mean? So is that that penalty would actually have a physical meaning, but you don't directly control it. Now, if I take the first derivative, let me not wasting too much time here. I will actually get back kd minus f from the first energy functional, but then I would actually also have k d times iq equal to 0. Okay? The important thing is this additional term. Okay? You see, it's very much like the Lagrange multiplier. The key difference is that this one doesn't introduce additional degree of freedom. Okay? You see what I mean? Only d is the unknown. But the expand is that I need to actually introduce a parameter k. K is a hard parameter. Okay? In fact, in most cases, if k is positive definite, your resultant matrix, which let me write it down in details, would be k would be simply this. Yeah, I won't make the detailed calculation, but you can easily do that. Okay, would be this energy, would be actually this system of equations. Okay. Now, notice that in this case, both the left-hand side and the right-hand side are changing, okay, for this system. And what you are actually looking at is this term, okay? We want this term to be positive definite. If it's positive definite, we can have a well-posed solutions, okay? It will be unique, okay? Does it always work? Okay, under what case would it not working? Now, penalty method is actually really popular because it's easy to set up and also it's faster because you don't need to put the Lagrange multiplier, okay? And you don't actually need to worry about things that you lost control because you have a block system. This one doesn't need to a block system, so it always look very appealing, right? Because I only have a single unknown, okay? And this single unknown actually doesn't make the system more complicated. However, imagine that I want to get back a Lagrange multiplier quality, okay? The constraint is very important for me. I want to make sure that I won't violate anything. I want to make this energy exactly 0. And I put k very large. So what will happen? Okay, so this one have eigenvalue. This one have eigenvalue. The eigenvalue are not adding together, okay, because you have a different characteristics polynomial. But in general, if your k is actually setting up too large, then you increase the spectrum of your eigenvalue system. Okay, meaning that some eigenvalue will be very big, some eigenvalue will be very small. Okay, so that won't be a problem if you actually use the LU decompositions or use the Gaussian eliminations. However, if you use iterative solver, then the conditional number is very important. Okay, because you're not actually going to find the LU, you're going to just approximating it or make a preconditional, blah, blah. And so it comes with a price that you need to control the conditional number. So how many of you already know what is a conditional number? Okay, conditional number is the eigenvalue of the symmetric part of the matrix. Actually, the largest singular values divided by the smallest singular value, and singular value is the symmetric part of a matrix. Okay? So you can also think about that if A is symmetric, if K is symmetric, K equals to KD, then the conditional number is simply the maximum, the eigenvalue that the maximum divided by the eigenvalue that the minimum, okay? And if it's positive definite, if your system of equation is positive definite, the conditional number is always positive, okay? Now, there's also another thing that in practice you need to control, and this is just my own experience, it's not the theory stuff. You need to actually always aware of the one-off number, one-off error. Okay, so your one-off error could be 10 to minus 16 or 8 or whatever. Let's make up something. And if your conditional number is actually 10 to 8 and your run-up number is 10, 10 to minus 8, you're in big trouble, okay? So you need to give some room for the run-off error and the conditional number, even if you use iterative, even if you use a non-iterative, even if you use the LU decompositions, which is slower than the iterative solver, okay? I won't talk too much about preconditional and solver. Maybe I'll talk about it in later lecture. But in general, one of the problem of that is that the unit you set up actually matter a lot, and you want to actually always look out the conditional number. In MATLAB, it will be COND plus the matrix. Check it before you solve the system, okay? I can give you an example. You can easily actually find a very big mechanically, let's not talk about bone mechanics. If a very hard system coupled with a very soft system, okay, like a bone that are with some meat that are surrounding it, the meat is very soft, the bone is very hard. If you solve the mechanical system, it naturally leads to a ill-conditioned system. It's really hard to solving it. Not because you don't solving it correctly, but because the nature of it is actually really, you have one system not that sensitive to perturbations, and you have another system super sensitive to perturbations, and you can't contribute to each other. So you create a master-slave relationship that if the hard system perturb a little bit, the soft system is going to fluctuate a lot. Okay, so for example, if you have a matrix that are 1 and then 1 prime 0, 0, 0, 0, 0, 0, 1. Okay, can you create a very unstable system? I just give you the first column. Can you write the second row so that it make the conditional number very high? So how do I calculate the characteristic polynomials? So now, this is not too bad, right? Okay, how to make it really bad? How do I jack up the, how do I make the entire conditional number very high? Actually, I can do something very simple. 10 to 100, okay? And I put a 1 here, so what will happen? I just make up some extreme number, okay? Or maybe I put a minor here, okay? So, okay, so actually, should I? Or maybe it doesn't matter, I'll put another minor here just to make it better. Okay, so what would be the eigenvalues? Can you already see the eigenvalues? It would be very close to 10 to 101, right? You see what I'm saying? This system is coupled, do you agree? Okay, this system is actually coupled. Okay, can you see that? Okay, but but does it matter how you rotate it? Sorry, actually, maybe you can rotate it a little bit, but you think about this, your first constraint, the x and y are actually almost have equal role, right? Versus in the second one have a gigantic role, one have a very small role, and you can actually imagine that if you calculate the conditional number, it will be very high, right? Okay, now in principle, even if I do it in Gaussian decompositions, I can solve the, I would definitely, so actually, let me say that. In this case, if you want to do the Gaussian eliminations, which one should I eliminate first? Now the order really matter. Okay, so let's put something x, y, and then a and b. Okay, just don't remember what is a and what is b. Okay, so I want to do the LU decompositions, or I want to have back calculations. which equation how should I write x in terms of y or y in terms of x? Which one would be a better choice? Yeah, I think the top one. Why is that? Yeah, because you can write it without losing that much accuracy, right? Versus the second one, it's essentially x played no role in the y, right? You see what I'm sorry? Is it? Sorry, it's the reverse, right? You see what I mean? Okay, so conditional number is very important. Now, what is the first options? What is the third options? The third option is the following. I will both use penalty and the Lagrange multiplier. Okay, this is actually the niche method, actually very common in contact mechanics. In which case, I will write, maybe I put a L. I just want to use different one. And then I will write FD, and then I would actually have the penalty term, but I would also have the Lagrange multiplier. Okay, so in general, when you look at it, it seems like you get the worst of both worlds, right? Does that make sense? Okay, you make it more expensive, but at the same time, you also modify the K, right? Okay, but why would you do that? You simply have that additional K. You actually come up that you can adjust the spectrum of the eigenvalue. You see what I mean? You can actually have more control. And in your pole mechanics problem, this is very important. When you actually try to solving it, sometimes you cannot solve the solution even for linear system. And make sure you look at the unit. For example, if your Buck modulus is 10 gigapascal and your permeability on the other hand is 10 to minus 14 meter per second, don't directly put these two things there. You're simply building a system very close to it, okay? So, but how do you resolving that? You just need to rescale both system, okay? You see what I mean? Just time a constant, and then you can actually bring back the eigenvalue very easily. In fact, that's the simplest precondition is simply have a row sum and then renormalizing the system of equations. Okay, so now going back to the mixed formulations of the pole mechanics, and we can take a short break. Okay, so there are two things that we want to do. One is to make sure that it's solvable, meaning that in the variational calculus, the minimizer exists and there's only one minimizer. Okay, and the other one is actually it needs to be stable, and not just stable by actually having a solution. Stable means you have a control, and that control should be maintained there regardless of the mesh. Okay. So being a row, having enough row giving you full rank is unnecessary but not sufficient for stability, because there's when you solve the mixed system, if you keep refining the mesh, you can actually originally have the full rank, and all of a sudden the rank, you just have a rank loss, okay? Okay, even there's also another detail that you need to pay attention is that if you actually perform reduced order integrations, you can also lose rank on the system. Have you guys tried that? Do you know what do you mean by reduced order integrations? Maybe I can explain it a little bit also here before the break. Okay, so this is actually a chord element that actually have 4 Kelvin point. Okay, and what does that mean is that I actually have a value, I have an integral I want to compute, and then let's say there's a length scale. Okay, yeah, maybe it's not a very good color. Maybe something like this. Okay, I'm terrible in drawing it, but I hope you get the idea. Now, I actually, if you're familiar with your trapezoidal rules, I would simply consider the level set of these 4 equations. I sample the f values of these 4 points. I will have 4 points of this, okay? So imagine that I want to compute integrations, okay? in this gamma of some functions, okay, that actually depends on x. Okay, so what is the right way to doing it? The right way is do it analytically, right? Okay, just integrate. Okay, sine become cosine, whatever. Okay, now, but if I actually think this equation is too complicated and I don't want to do it analytically, then what should I do? Okay, so in 1D, there's a generalized trapezoidal rules. Okay, let's say I have these functions. Okay, I just sampling it multiple point, and then I say that, okay, I just say assuming this is the average, and then I assign a weighting on it, and then these three brought the area would be approximately the original nonlinear functions area, right? Okay, so to do that, if you assume a polynomial, you can find out the coefficient of W, and this integration from your finite element, you probably already learned it, is that it's going to be the weight of the functions at that particular Gaussian point times the function value of that Gaussian point. Okay, this is called the Gaussian point. If you use the Gaussian quadrature, you can use Samson rule, you can use all the other thing, okay? Okay, if you use 1 point, okay, if you use 1 point quadrature, then what happen? If you use 1 point quadrature, you just take the average at the middle, you just midpoint rules, you just assume the whole thing is just a rectangular block, okay? And you just assign a weight to it. That's it, okay? Now, why do I say that is that when you integrate the solutions, you have multiple choice, you can think about this. If my function look like this, okay, how many Gaussian points do I need? I need a lot of points, basically, and I need a very refined way. In fact, in extend finite element, even in 1D, I want to integrate this, okay? Or maybe not exactly like this, some kind of jump. Okay, maybe something like this. So how do I do it? Okay, now if I actually, then I need to think about how do I paste those points, and then what is the way to doing it in order to get the closest solution. So the positions and the weight of that Gaussian point will affect the integration. Okay, in 1D, you don't really care about it because I would recommend if you want these solutions, I solving it analytically. In fact, I did that in the 1D finite element code that I can share with you in MATLAB. So in 1D, you just do it analytically, you should be fine. The check function is not too difficult to integrate. It's linear anyway, right? Now, the reason I want to go back to this is that sometimes you do the reduced order integration to actually remove something called locking. But at the expense, you may actually relaxing it too much so that even though everything is set up correctly, your finite element doesn't have sufficient constraint. It will lead to a singular problem. Okay. The other opposite is over-constraint. What happens when you have over-constraint system? You have no solutions, okay? If you over-constrain, you cannot fulfill all the solutions, okay? Then what should you do? If you have 3 unknown and then you have 4 constraints, what should you do? You either pick 3 of them and find the unique solutions, that will be one way, or you can actually solve the least square solutions, okay? So imagine that A is a rectangular matrix, okay? So AX equal to B could be written, but the inverse of A doesn't exist, right? But remember, ATA is also a square. So ATAX times ATB always exists. Then this is called the least square solution. It's not the actual solution, by the way. You may get the different solutions, okay? Compared to AX equal to B, but you can actually get some solutions, okay? So going back to that, sorry, I think I'm a little bit out of topic. So I want to actually define the solvability in a more absolute sense. A system is solvable if AX equal to 0, imply that X equal to 0. Okay, does that make sense? It simply implies that you actually doesn't have the null space on that matrix. Okay, sorry, you do have a null space. Basically, it's nothing. It's an empty set. Okay, sorry, it's also not an empty set. I'm also incorrect. You have exactly one element, and that element is everywhere 0. Okay, that should be the only element in that null set. If your null set actually have non-trivial bases, then it's not solvable. Okay, does that make sense? Okay. So what it implies, m minus 1 must exist. And then what we calling that m is actually k, g, t, beta delta t, omega. And this is actually for the continuous problem. And then there's a special case that are called undrained. Okay, what is undrained? Undrained is when the permeability is 0, there's no way for the water to move. If the permeability is 0, there's no need to solve the Darcy's law, the water just trapped inside. In this case, you have a specific system or matrix that actually doesn't have the time domain, but you need to solve this system of equations. Okay, and this is 0. So to give the full rank, what is the hope of getting the full rank if this low column is 0? Okay, now let me give you a counterexample. If this is actually like this, how do I get the full rank of that, let's call it B matrix. Or maybe let me put another one. Let's call it the D. Okay, so if it's the broad matrix, but then the off-diagonal term are all 0, how do I ensure that D minus 1 exists? So what is the eigenvalue of D? Josh, I think you know the answer, right? It looked like you. Or you just happen to move your body. Just a coincidence. I thought you were sometimes students want to raise, but then they actually just want to Okay, so the eigenvalue of D is simply the eigenvalue of K and eigenvalue of A, okay? So because of the off-diagonal matrix, you can try it. The characteristic polynomial doesn't affect of K and A are decoupled because you don't have off-diagonal term, okay? If you write those factorizations, they just independently exist. Now, if you have this, but unfortunately we don't have this system. In fact, if you have this system, how are you going to solving it? You don't even have to bundle them together. They're independent, right? You see what I mean? They don't have any coupling terms, so why bother to solve it together? You can just... Now here, they're coupled. And as you can see, I can assuming that K have the full rank. Now, in order for M to have the full rank, G has to provide all the extra rank so that I maintain the full rank, okay? You see what I mean? So this one important concept is that if K is stable, then what you actually rely on is the property of G matrix, and G is a rectangular matrix, to actually give you the full, the sufficient dimension in the column space. Does that make sense? Okay, so the logical, let's go back to a little linear algebra. In order to solve the problem, you need to have the full rank. What it means is that all the column space has to be independent of each other, right? It doesn't matter, it's a symmetric matrix. So row and column space are actually identical, okay? So I need to have full rank, okay? Now I know K has full rank, so in order for the whole thing have the full rank, G itself also need to give me enough rank so that I don't lose any rank, okay? You see what I mean? Okay, and then this full rank has to be kept regardless of the mesh I choose, regardless of the Gauss-Born integration I choose. So if I choose a different integration scheme, I will have a different G property that may or may not give me full rank. You understand what I'm saying? Because the G, what is the G coming from? It's coming from solving that B matrix integral, right? Okay. I put different number of Gauss-Born, I will use a different G matrix, okay? And if I use a different space for N and B, or for displacement or pressure, I will also get a different G matrix. So the magic of solving a mixed system stably is actually not, well, you need to always make K stable, but it's very easy to make K stable. You just need to have an elasticity matrix that are tensor that are positively definite. But what actually hard is actually find the right G so that I give you the full rank. Okay, you see what I mean? And you need to actually think about how do you integrating it, what is actually the space for n, and is the space for the n for the degree of freedom of pressure compatible with that B matrix that are actually used for the solid. What do you mean by compatible is that they give you the full rank, okay? Anyway, so I think this is actually the time for a break, so let's resume at 11:30. Okay, shall we do that? And I'll go to the mathematical part. So I haven't go to any mathematical part on the other hand. Okay, let's take a break here. Resume the meeting. So we talk about the relational calculus, very brief overview. I mean, if you like, you can take a whole course on the relational principle or actually on Euler-Lagrange equations, both in mechanics, in physics department. So that one you just mean to be devised to talk about the mixed formulations. Okay, so to give you a deeper sense of what is it about. And one of the major difference from the relational calculus that we know is that in the case of actually the unconstrained optimizations, you are actually solving an optimization problem. In the case of constraint optimization problem, sometimes you give rise to something called a settle point problem. Okay, what is a settle point? Let me draw a figure. So I let you draw a figure as as none and my colleagues John know. So okay, let's say I have a minimizer. Okay, I have in a 3-dimensional domain. I simply want to find the smallest point, and this is actually called a minimizer. The same thing for the maximizer, you're just swapping that geometry. Okay, there's something called settle point, and I hope that I can draw it properly, and I'm actually not really good at drawing, but imagine that you have two axes. Okay, and this is actually not a physical axis, just a degree of freedom axis. So in this axis, I want to minimize. Okay, so there's a multiple slide. I want to minimizing it, and then they have okay, and then on in another axis, so along this axis, x or maybe, and along this y axis, I actually want to maximize. If I actually linking all those points together, I don't know how to do that thing in your face. I have actually, if I look at it in one axis, I'm minimizing the problem. If I look at the another axis, I'm maximizing the problem. Okay, do you actually forgive my drawing? I know it's terrible, but this is actually called a settle point problem. Actually, settle point coming from the thing you actually want to imagine you want to ride a horse. What is the thing that it's called a settle, right? So that thing, okay, the settle point is actually the point where you simultaneously minimize something and you're maximizing something. Okay, this come up in the pole mechanics problem, in the stroke equations, in the incompressible elasticity. You're simultaneously maximizing the dissipation and minimizing the free energy. Okay, now I just want to, so here and this is actually related in that sense to the relational calculus, that in a constraint optimization problem, oftentimes you rise into this system. And you can see the exploration is much harder because here I just start here and I just try to go all the way to that settle point. Here I actually need to think about how I investigate and then to reaching this point. And one of the key difference is that for different finite element, you may or may not have unique solutions. Okay, so why is that? And this is actually the problem that have been solved by three distinguished mathematicians. Sorry, I don't know how to pronounce the first one. Can anyone try? She's actually a Russian mathematicians that I don't know. Ladies in since what? Sorry, forgive me. Okay, I really try. I mean, I'm not trying to. I have a lot of respect for her. I just really don't know how to pronounce her name. Babushka and Betsy. Babushka is actually a professor in UT Austin for many years. He also invents one of the first people to form the generalized finite element, which is a form of extended finite element. Another one is Betsy, the Italian mathematicians. They actually independently discover that, okay, when I use mixed finite element, I need to find the right combinations of discretization to make it stable. Okay, it's not the element that make it stable, it's a combination between how do I discretize P, pressure, and displacement that make it stable. Okay, is how do I make them compatible. Okay, so here, so this half of the course need to introduce, as you would actually imagine, some concept of mathematics, so I'll try to do it slowly. If I go too fast, let me know. Okay, so let's go back to history where we are all very young, if we're actually born at all, in the 1990s. Okay, so we have a system of equations that we try to solve, which is actually resemble what we have today in both the linear, elasticity, and or stroke system. Okay, we want to solve this. And we want to, not only that, we want to make sure that the solutions are unique. And this is actually the question that Betsy and Butter, there's a E here, actually try to analyze. So D is actually the nodal unknown for displacement, and P is actually the nodal unknown for pressure. K is actually like what we described, N1 by N1 square matrix. And G, on the other hand, are actually a rectangular matrix. Now, it could be square, but it will be just by accident. In general, they are rectangular. Okay. Now I have two systems of equations. The first one is coming from the Lagrange multiplier term that we talk about. You can think about the GTD equal to 0 as a constraint that actually come up from the Lagrange multiplier. Okay. Now, if you look at the system, there is nothing in the second equation. You don't even write the P there anywhere, right? You notice that? I just say divergence of V or divergence of U equal to 0, okay? Now, there's a few observations they actually help to solve this problem, okay, that I actually set up the analysis. So in general, N1 is greater than or equal to N2. Okay, so this is the assumption we made. Why is that? We simply have more displacement degree of freedom in general. Okay, it could be a special case where N2 is greater. Okay, but in general, N2, we expecting that the system of K matrix, the K matrix is larger than the 0 matrix. Okay. Okay. If it's actually the other way around, that could also be another issue that you need to think about, okay? And then the second one is that is the important property of the G. Okay, so what we actually want is that if GP is actually equal to 0, then we want that P is actually 0. We want GP equal to 0 imply that G equal to 0, okay? And this may or may not happen, okay? You know what I'm saying? In general, if G is actually a diagonal matrix, square matrix, of course that will happen, right? okay? Or maybe not necessarily identity, but a diagonal matrix, that will happen, right? But you can also have something like losing rank, then you would actually come up with a P that are not equal to 0, but GP equal to 0, okay? This is a situation we want to avoid. Now, how do I actually write it or analyzing this in a more formal manner? Then I would say the following. What I actually want to do is define the namespace or the kernel. Here, I would actually use both the matrix, algebra, language, or actually inter-exchange with the kernel. They're not identical, but here, for the argument's sake, I just say that I've just used the namespace and kernel in interchangeable manner, just for simplicity. The first thing, then, what we actually want to say is that we want to define a space called K, which is actually equals to the kernel of GT. Okay, what is this? It's the following. I want to collect all the vector that are actually in the data of the dimension of n1, okay? n1, not n2. That gives me GT of V equal to 0. Okay, so K is a kernel, or namespace is a collection of all the vector that actually give me GTV equal to 0. Obviously, V equal to 0 is one of the collection, right? Does that make sense? Okay, because if V is actually equal to 0, no matter what G is, GTV is going to be equal to 0, right? This is not our concern. Our concern is to find out whether there is some other V that also cause GT equal to 0, okay? Do you guys understand that? Okay, let me give an example. If I want 0, 0, 0, 0, 0, okay, so what will happen? Okay, you get it? I will simply, now I will introduce a namespace that are actually not 0, 0, right? Okay, but 0, 1, right? Is it? Actually, let me do it. So if G equals to this, then it will be the transpose of 1, 0, 0, 0, 0, 0. Okay, and then I would simply would have so if V equal to 0, 0, of course GT equal to 0, okay? But if V equals to G0, 5, this thing would also be equal to 0. So does 10, so does 10.2, so does any number, right? Okay, this would be an example that the namespace contain element other than just 0. Okay, does that make sense? Okay, and if you have it, then do you have a unique solutions? Right, you won't have a unique solution for the following reasons. I think here I should put the T here, and then that should be just G. Okay, so you won't have a solution for that reason is that you now admissible a family of solutions that actually make GTD equal to 0, but D is not even necessarily 0, okay? Sorry, D could be something else, okay? Now, if this is actually admissible, then anyone, so then any combination of that would also be imply GT equal to 0. So this one can even be just be a variable, just be any real number, okay? So that would actually affect the stability. So let me. Okay, so our first job is to identify this space, just give it the name, okay? So do you guys, so in order to not losing you, do you now get the concept of the kernel of K, of the GT? It's simply the namespace. So basically here in translate to English is that any V that are actually n one-dimensional vector that makes GTV equal to 0, okay? I don't care what it is. It could be 0, it could be something else. I just have the whole collections, and I call it kernel of GT. Okay, do you understand that? Okay, yes. So now, what is the dimensions of this? What is the dimensions of K you want? What is the individual row vector you can hope to have? What would be the dimension of that? That K? It would be actually in the, well, K would be simply n1 times n2, okay? It's a rectangular matrix. Now, there's also another conditions we want. This is what we want. And then there's also another thing we want is the following. If D is actually belongs to this kernel, okay? Does that make sense? So if D, so first I define a kernel, okay? The kernel is any GTV equal to 0, okay? So far so good? Now the next thing I want to consider is that what if in that D, if D is a collection of that kernel, okay, one of the example of that kernel, okay? I don't know whether, right now, I don't know whether it will be just 0 vector or it will be something non-trivial, okay? We don't know yet. But what do we want about this? For all the VK that are also in the kernel. So this is every vector that are in the kernel space, and D is actually also in the kernel space. Okay, D and V are not necessarily the same vector, but D and V are both in the kernel. Okay, so what do we want this is that we also want this equal to 0. Okay, do you see why? Well, anyway, that would always equal to 0. But what you actually want it to imply is that we want it to imply D is actually equal to 0. Okay, so if D is actually belongs to the kernel and every V is actually belong to the kernel, we want this VTKD equal to 0 simply imply that D itself can only be 0. Okay, do you get this? Now that's what sounds very ambiguous, but let me think about this. K is a positive vector. K is positive definite, right? Right? Okay, K is positive definite. Do you agree? Okay, what is KD give to you? It's a vector, right? Okay. So VD KD as a vector equal to 0. What does it tell you? What is the relationship between VD and KD? Basically, the dot product is 0, right? Okay. In what case would the dot product equal to 0? Huh? Orthogonal to each other. Very good. Okay. So why do we want that? Well, we know this has actually happened, but we want that when it's orthogonal, it's only because D is actually equal to 0, but not for anything else. Okay, why is that? So imagine that D doesn't need to be equal to 0. So what will happen? So if D is not equal to 0 and K is positive definite, then what is KD? KD is non-trivial, right? Some kind of number, okay? But if I have some non-zero KD, that actually times VT that are not equal to 0, what does that tell you? You also lost the control, right? Or the perturbation, right? Because if you consider the counter example, okay? Consider the counter example. Maybe you can see it in the opposite way. If K is not equal to 0, but VTKD is actually still equal to 0, so what will happen? I would also lose stability, right? Because this is equal to 0. That means if I times alpha, that would still be equal to 0. All right, alpha can be any number. I will take it out. Okay, so do I have unique solutions? I will not have unique solutions. Okay. So now let me think about the problem in a more formal language one more time. Okay, I just want to layer onion and just remove it layer by layer, and I hope that by now you still have the onion with your hand, still know what I'm talking about. But if not, I would actually try to talk about it. Now, what is the stability in pi? Stability is actually related to some kind of control if I don't do a lot of math terminology or jargon. What we actually want to do is the following. If I have a mx equals to b, and then I actually have a perturbations of x, and then I think that will lead to the perturbation of b, or if I have the perturbation of b, I will actually lead to x is actually changing. The key idea is the following. I want to say that if my perturbations in the forcing function is actually somehow small, okay, remember that it's not a formal language, it's just to explain the idea. Then I want this one to be also small. Okay, does that make sense? Okay, if I've actually picked up, I know AX equals to B, but I want to make sure that if I change a little bit of B, I can guarantee that the change of X won't be suddenly very gigantic. Okay, does that make sense? Now, why do I hate those non-trivial Noon space? Not that I hate, but I just don't want it to exist. There's a two difference between the two. There's a very important difference between the two. Okay, if you have those Noon space, can you still control X? You cannot, because I can put any alpha times that Noon vector there, it will still be the same system, right? Okay, I cannot use the delta B to control the delta X anymore, because delta X doesn't depend on delta B anyway, right? You do remember that? It's a Noon space, so it doesn't really depend on the Noon hand side. The Noon space are actually all the initial vector for the AX equal to 0, right? So you want AX equal to 0, you want that X to be only be 0, not anything else. Okay, does that make sense? That's why you want that positive definite on the A matrix. Okay. Now, just to test the idea, how do I quantify what is big and small in your calculus? How do you give you a sense of what is a big vector, what is a small vector? How do I measure? Okay, how do I measure money? How do you say that someone is rich and someone is poor? I have a lot of money in the bank, then I will be rich. I don't, but for the argument's sake. Okay, this is a scalar, right? So there's a plus or minus side, okay? How do you say someone is happy or sad? It's much harder, okay? So you don't have a space to define that, okay? But let's say how to measure a student is good academically in an undergrad? Or yeah, you compare the different bases, and then this basis as a measure is good, then you say the overall thing is good. Okay, maybe it's still too much. How about SAT? How do you say someone have a good SAT? You have a quantitative part, you have a writing part, you have a verbal part. So three of them are actually some kind of basis, right? How to define what is good. All of them score very high, right? Okay. So anyway, what I want to say is that in a vector, so you need to not only at the individual, you cannot directly using the component magnitude to measure how good this thing is, but you also need to actually provide a suitable measurement, and that measurement is actually called norm. Okay, and norm doesn't actually give you the norm doesn't necessarily give you the sense of distance, but the norm on a vector space gives you the sense of distance. Okay, you see what I mean? If you have this rotation curve, then the distance is actually this, and then the norm between two vectors is a straight line. Okay, they are not identical. They will be identical in a very small distance. Is to check the idea. Okay, we need this to measure the big and small. Is that I want to make sure that if B is actually changed very small, X is also changed very small, I won't lose the control. Okay, so that ratio. So, but to go back to that, to measure distance, or actually a size or whatever for vector. Okay, we need to use something called norm. Okay, what is a norm? There are multiple different norms. So let V being an n-directional vector review component. Okay, the classical way you actually measure the norm that you learn from your undergrad, just saying norm, is actually the L2 norm, which is also called the Euclidean norm, which is actually, you can write it like this, sometimes you just write 2, and simply this is just the square of all the square root of all the components combined. Okay, it's also called the Euclidean distance. Okay, so if I have a distance go here and a distance go here, the length of this line is actually the L2 norm. Okay, so let's have that beautiful relationship to it. Is the shortest path between 2 points in a flat surface. Okay, not in a curved surface or in any other thing, but on a flat surface, they are the shortest distance. This is actually called the L2 norm. Okay, in your finite element class or in a machine learning, by default, you would often use the mean square error. And this is actually an example of assuming that you're dealing with some Euclidean vector and you're using the L2 norm. Okay, so let me ask you a question. If you want to take a taxi from here to Chinatown or Korean town or whatever, do you think that the Euclidean norm is a good measure in New York? Do you think you can using this, which norm is longer, and then make a prediction on the Uber price? Why is that? Well, first of all, New York is a grid system, so you are not going to go like this. Okay, you are not in a helicopter. If a helicopter, maybe that makes sense. You're going to go down and go to the other side, right? And not only that, to go down and go to left and right, if you live in New York long enough, you will see that it's very different. Okay, you see what I mean? It's much easier to go up and down and left and right, in my opinion. You may disagree, but if you walk really fast, maybe it's similar, but I find it easier to go up and down. Okay, so you need to introduce different bias. So what I'm saying is that you can measure the norm in a different, you can measure the distance for the vector in different way, not just the L2 norm. L2 norm is one way of the measuring it. And if you pick a particular norm, you actually pick a particular perceptions of that vector space. Okay, and then the space become normed space, which means that the norm are actually restricted to a particular way for you to measure the discrepancy of two vectors. Another one that I want to mention, and that could also be very different, important, is the L1 norm. And the L1 norm is actually simply the absolute value add together. Okay. By the way, why don't I just add all the components together?
They may cancel each other.
Yeah, they may cancel each other, and they may even go negative. Okay, this is a property we don't want for a norm. A norm could not be negative. Okay, so that's why you put the absolute value there. And then there's another norm, P norm, or the LP norm. Basically, it's just a generalization of these two special cases, except that now I would actually times it P time, and then take the root respect to 1 divided by P. Okay, does that make sense? Now, there's also an extreme case. What if P go to infinite? So I want to ask you, if P go to infinite, what happens? Huh? You get the maximum? Yeah, okay. Excellent. You learn it before, or you think about it on the fly? You just know. Okay. Okay. Okay, so think about it. Does that make sense? Okay, I take it P time and then I divide it by P time, so only the maximum eventually survive, even though it changed a little bit. If P go to infinite, right? So the higher the P I go, and P is even number, okay, not odd number. Okay, just imagine. Okay, actually it doesn't need to be. It could be odd number because I put the absolute values. So the higher the order I use, the more sense the number, the operator of the would actually separate them apart, right? You see what I mean? 1.3 time 1.3 to 10 would be actually have much more difference than 1.5 to 10, and minus 1.4 to 10 would have much longer distance than 1.5 for 2 and minus 1.2 for 2, right? So anyway, so I think you get it. Okay, why do I actually need all these different norms? Is to measure, is to check. And bear with me, I may not able to finish in 40 minutes. If that, I'll go to it on Friday a little bit. But I think this is the core of that mixed formulations. Okay, if you don't understand it, it's really hard to build a mixed system. Okay, so there's another concept that I really want to talk about, is that all of these norms are equivalent. Okay, what do I mean? Do I mean that the number are identical? No, of course not. You use a different distance. Okay, what it means is that they can be bound by each other, so there exists a scalar where you can actually make one the upper limit of the other if you times that alpha, and alpha must exist in order for the norm to be equivalent to each other. Okay, does that make sense? Okay, so what it means is that you cannot have one thing go to infinite and another one still finite. That's all it means. Okay, you see what I mean? They have to go to finite. They have to become infinite at the same time, in a very informal way to say that. Does that mean? Okay. So for example, if I have a maximum norm would always be smaller than the L1 norm, right? Do you know why? It's obvious. The maximum norm only have one term, and then the L1 norm keep all the other terms still there, right? So I simply have more positive terms, so of course it will be bigger, right? Okay. Now, but will they go to infinite? If one go to infinite, what happened to the other one? Okay, so here. Anyway, so what we actually want to say is the following. If you use the equivalent norm, you can perform an analysis with the different norm, and then you can actually, based on the analysis, you can actually formulate your conclusions in that particular norm space. And there are two important concepts I want to talk about, and they are actually very close. The terminology is very close, but they are actually very related to the inf-sup conditions. Okay. The first one is actually the infimum, and that one is actually, you write it as INF. And what it means is the greatest lower bound of a set. Okay? Does that make sense? Okay, so let's say I have a set that I actually have 1, 2, 3, blah, 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 blah. Okay, what is the greatest lower bound? So the element is an integer, right? Non-zero integer. Okay, is 0 at the boundary? You can argue that 0 is actually next to the boundary, but it's not part of the set, right? Okay, so to add the collections, only the smallest one is 1, right? Okay, so this is actually the greatest lower bound for that set, because it doesn't contain 0, okay, and it doesn't contain all the way to it contains something approaching infinite, but the infinite is also not contained in this particular case. Okay, so basically is a lower bound that are actually just at the boundary. Okay, does that make sense? And then there's also another concept that are very important. Is a supremum, which is actually, we write it sup. Okay, and then the word game is actually inverse. This is the least upper bound. Okay, so in this particular case, integer number, it won't contain infinite, but then the least upper bound will be something very close to infinite. Okay. Now, so these in and sup conditions are actually combined. It's called the in-sup conditions, and that's another name for the Betsy-Babushka conditions. Okay, it contains of in and the sup because of the settle point problem. Okay, you see what I mean? And let me give some example to actually explaining that. So example 1 is this. S is actually what is a set of a positive integer. In this case, one thing that are very important is that the int of S is actually simply the minimum of S in that set, and that is actually 1. Okay, so far so good. Now let me define another example so you can see the contract. Let's say S is a set, collections of all the positive vector. Okay, positive real number, not a vector, that are actually under the conditions of y equals to 1 divided by x. Okay, and x is also a real number. Okay, so in this case, what is the in of S and what is the minimum of S? What is the minimum of x? X is actually simply also a positive real number. What is the minimum of that set y? What is the minimum? It can always get smaller, right? Okay, but you think about it, does it contain 0? It doesn't contain 0 because x are limited to be positive real number, right? It's very close to 0, but it's not actually 0 is not even in that set, right? You know the difference between the two? Okay, so in this case, the bound that actually contains the entire set is actually 0, but then the minimum doesn't exist. Okay, because in that real number, I can always find something that are bigger and closer to infinite. So the one divided by a very big number will be even smaller. Okay, you see what I mean? So you will never get to 0, but by the time I get to 0, I'm already out of that set, right? So you see what I mean? In that case, the bound doesn't even contain there's a room between the actual bound and then the smallest element. You know that is actually the small difference between the minimum conditions and the inf conditions, which is very important here. Okay. Otherwise, you would call inf-sup condition min-max conditions. Okay, you see what I mean? Like everything, sometimes it's a tiny thing that kills us. But, okay, so why do we actually want to care about this? Okay, so now remember that. Okay, but in an informal way, if you help you memorize, this is actually related to the minimum of the set, but not exactly, because it's actually the bound. This superior is related to the maximum, okay, but it doesn't contain the element. You see what I mean? The difference is whether you contain that in this open set, okay? Why do we actually want to care about that is that I want to make sure, I would want to learn the property of M. And I actually need this I actually need an additional mechanism to measure the operator M. What is the property of that M instead of director X or B. Okay, so that brings us to the key idea, next concept, the matrix norm. Here, what we are talking about is not the fabulous norm that you actually just time all the matrix, but from an operator sense, what is the image that the M could provide? Okay, here we will use the following concept. You have an M operator. Okay, and I was saying that the matrix norm is actually the superior of Y, actually of My divided by the norm of Y. Okay, so what is that? What is that physical meaning of that? Okay, so this, remember, is somehow related to the max. So I think first thing to understand that is a language. Okay, you need to translate it to English or whatever language that can comprehend. So what does that mean? Okay, in order to measure the norm of the matrix M, okay, I need to actually find a particular Y, okay, such that this whole thing becomes maximum. Does that make sense? Okay, why do I want to do that? Why do I actually not finding the minimum? What is mx? Mx equals to b, right? Okay. So why do I construct the norm that actually care about the maximum? Okay, let me draw a figure. Maybe that would explain this a little bit better. So I have this Y matrix. Okay, just for analog, Y is not a scalar. It's actually a multi-dimensional vector. But let's say I'm just consider changing some magnitude of Y and then I have the m that are in these directions. Okay, so this is actually the M matrix. Sorry, this is the matrix norm. And then if I measure this in all the other physical or in all the other property, let me do it. Let me repeat. So let me compute the my derived the vector norm of my. My is a vector, right? Do you all agree? Okay, and y is also a vector. If I actually compute that, I get a ratio between what is y and what is mx, my, which is supposed to be, one of them would be b, right? Do you agree? One of them would be b, okay? If y equal to x, then if y equal to x, then my would be equal to mx would be equal to b, right? Do you agree? Okay. Now, I actually compute this randomly just based on m. I don't know what is b, and then I would obtain this landscape. Okay, it has a lot of up and down, just for the argument's sake. Okay, so in a particular case, here, I would have y equal to x. Do you agree? Okay, do you agree? And what is this y-axis? That would become b divided by x, or b equals to y, because y in this point is equal to x, right? Do you agree? Okay, so what we want to see is whether mx equals to b have any, I can control that operations, okay? You remember that? Okay, this point you get it? Okay. Now what is this point? Actually, let me make it bigger. What is this point? This point is the maximum of this whole curve in an accurate sense, because I haven't considered whether it's actually the boundary, whether it's contained in the set or outside. But what is this point? This point is the matrix. This is actually the matrix norm. Okay? So why do I want to put it higher? Now this one will give me y star. I still have time, right? Okay. Sometimes when I talk to myself, I can talk for a very long time and I forget the actual time or what it is. So, okay. So now, what do I use this distance for? Okay, for the analysis. Now, back to that question. Why don't I pick this point? Is any point lower than this b divided by x useful at all? Now, there's a very one important property that I want to emphasize here is actually this distance. Okay, so if I take y equal to x, like this, I will get my equals to b. And hence, what I can assure you is that the M matrix norm is actually greater or equals to the b divided by x, right? Why do I actually assure that? Why do I actually knowing that M is always greater? Yeah, exactly. Because I'm actually actively seeking the highest point. I don't really care about where is B, okay? B, give me if y equals to x, give me the solutions. But here, I'm actually just want to know in the worst case scenario, or actually if I amplified it the most, this is actually the measure I have with the matrix norm. Okay, so now let's go back to that idea. Do you see that I have a b here and I have an x here and y, and then the norm of b divided by the norm of x? What does that tell you? Is that if I change x sorry, if I change B, what is the change of X and vice versa, right? This gives you the ratio of the B matrix, sorry, B vector and X vector. And I want my norm to be defined such that if I define the norm of the operator M, I would actually always be greater than that B to X so that I can have the worst case control. Remember, very important. And this bound is actually more useful than the other way around. I won't use the minimum. Okay, you see what I mean? Now, what happened to the inverse? That's also another way to think about it. Okay, what is the inverse of the M vector? So the inverse of the M vector would be the supremum of the related to the Z vector, where M minus 1Z divided by the norm of Z, right? Okay, so far so good. It's just the definitions of the matrix norm. Now I will draw the figure of this. And again, Z is not a scalar, but for the argument's sake, I just say I changing the Z in multiple different directions, I get some landscape of it. And then what I would have is that at this point, Z would be equals to the delta B. Okay, at this particular point. And then I would have another point that are actually here that is in some Z star, and I don't know what Z star is. It's not necessarily related to the particular solution I'm interested in. But then it will be the M minus 1 norm. Okay, and this particular point, only this point is actually the M minus 1 norm. All the other points in the y-axis are actually M minus 1Z divided by Z, but they are not necessarily the norm itself, the matrix norm itself. So only this point, only this red point is the norm. Okay, so what I actually want to say is the following. Now let's go back to our original goal. I have the Z and then the p-derived. Okay, now this is not equal to B, but a small change of B. Okay, what would be the corresponding change of the X? So I want to know if I change B, how much change I would have for X, right? Okay, so now AX equals to B, so the inverse is that B equals to minus 1X, right? Okay, does that make sense? So, sorry. Mx equal to B, so M minus 1B equal to X, okay? Sorry. Okay. So now, if I actually look at this, then I can say that the change of the inverse, the matrix norm, the perturbations of the X divided by the perturbations corresponding to B is actually always bounded by the inverse of the M minus 1. Okay? Can you see that? Just by the definitions of this. Okay. Now, what is the next step? Is the following. Let's say I start with delta X, and delta X, according to our previous derivations, is actually smaller than the M minus 1 B times the norm of the perturbation of B, okay? Now, on the other hand, X is actually greater than 1 divided by M times B. So this coming from our second M minus 1 derivations, this one coming from the M derivations, okay? So if I actually want to write, if I perturb x, what I'm saying is that I'm going to have this, I'm going to have the perturbations to x, I'm going to change this ratio, and what will happen to this? What would happen to this is that, so I know this side is greater than this side, right? Okay, so if I actually have, if I actually want to compute this, so do I actually know what happened to this side? Can I actually derive the equality coming from this? So let me give an example. 2 is greater than 1, right? Okay, I think we all agree with that. So 1 divided by 1, however, is actually greater than 1 divided by 2, right? Okay. So now, how do I combine these two equations? Okay, I can put this part on the top and this one put to the bottom, because you know what I'm saying? Because A greater than B implies that so A greater than B implying that 1 divided by B greater than 1 divided by A, right? Okay, you get what I'm saying? Okay, so just like 2 is greater than 1, but 1 divided by 1 would be greater than 1 divided by 2, okay? So, just want to explain that very slowly. Now I'm combining this. Okay, so, and then have these equations. Yeah, which is quite nice, I would say. Why would I say that? Because now I can write the ratio between the perturbations of the solutions divided by the solution itself is always bounded by the matrix norm of the operator, and then the inverse of times the norm of the inverse operator times the perturbations in the right hand side divided by the right hand side vector. Okay, they're not equal to each other, by the way. Okay. So far I did not lose you, right? You still get it? Okay. So let's take a look at this. Okay. Now this term has a very important name. This is actually called the stability constant. Okay. Now the questions. Do you want this number very big or very small? Do you want it to be very big or very small? Let's take a look, okay? Let's take a look, shall we? And then we're already running out of time. I still haven't, everything I did not even start the inf-sup condition yet, but it's actually work for KD equals to F. But I think that gives you more in-depth understanding on the stability. Okay, so now take S equals to the matrix norm, and then the inverse of the matrix norm of the is inverse. Okay, by the way, S is not equal to 1. Okay, I hope you can see that. M dot M minus 1 is actually equal to identity matrix, but these two norm not necessarily equal to 1 all the time. Okay, it could, but not necessarily always the case. if I do this, then the difference between the two, or they are actually bound by that S stability constant. Okay, so here you can say that if S actually exists, so the X is somehow under control of the B, right? You understand what I'm saying? The change of the B, I can somehow manage to control the change of the X. Now let's take X equals to m minus 1x. I think you all agree with that. And just basically doing nothing. And then let y equals to m minus 1x. Okay, so what it implies is that x is actually equals to my. Okay, and if I take the norm again, which would be the max or the supremum of this quality, then what I would have is that I will have my greater or equals to my. Okay, do you see this? Let me stop here. Do you see this? How do I rewrite this to this? Well, this is already the maximum, right? So anything that are not at the maximum, meaning that the other side is greater, right? Do you understand what I'm saying? You get the idea? Okay, I'm basically writing it in a two different way, okay? You see what I mean? And then I times both time by the norm of y, that's it, right? Do you see that? Okay. Now this one is simply x. Okay, this one I put it back into m minus 1x. Okay, so, and what I would have is that I will have m times m minus 1 dot x on this side, and this side I will have x. Okay, so I take out the norm of the x, so I would end up with is that 1 has to be greater than m, the matrix norm of m, and the matrix norm of the m minus 1. And that is actually the stability constant, and the stability constant is always greater or equal to 1. Okay, does that make sense? It's just algebra, so okay, I'm a little bit slow on defining that. So far so good, but you're still with me. Okay, so I haven't able to finishing that. I think that I haven't finishing it, but I think it's okay. I'd rather do it like this than actually rushing through and you don't understand it. But so far, from point 1 to point B, do you understand the whole derivation so far? Okay, then I can actually give you a little bit of discussions, and I think in that case, let me use the Friday to finishing that, and then we shorten the tutorial sections for the computational if it is okay. Because what I feel is the following: if I don't tell you how to find the space, you may actually able to solve the problem, you just don't know why it works. Okay, for you it will be just like, hey, let's use Taylor hook and it worked. Okay, I remember that Taylor hook meaning that it worked, but you don't know why, and that's not the purpose. Okay, so what if I ask you to formulate a new finite element? Or what if your boss asks you, hey, I really hate the Taylor hook for no reason, I want a composite element. And you say, hey, I don't know, I only know Taylor hook work, I don't know why it worked, and so I'm stuck, right? So that's not the point. So what I want to do is that I know that in the Phoenix or in the other code that already have a predefined composite space, you can make it work. I want to tell you the details of why it works, okay? And then when you're using it, if you like, you can always program in MATLAB or in Python in details, but if you cannot, at least you know why it works, okay? You don't want to be like make the course like answers or abacus tutorial where you know how to pick all the twists and make it work without knowing understand the underlying idea. Now here, there's a few things I want to talk about. We need to talk about the inf-sup condition, which we haven't even talked about it. But before we actually introducing that, we need to introduce another concept called dual norm. Okay, and then we actually want to introducing the the idea where you not only consider the matrix, the operator of M applied to X, but what happened to the Y part on the left hand side. Okay, you see what I mean? So that will require more discussions, but I would actually also would talk about that. Okay, so we need to understanding the dual norm, and from the dual norm we can derive the inf-sup conditions. In the literature, you will find that people argue that inf-sup conditions and actually not the same as the Betsy condition, which is different than the babushka conditions, and which is actually also different than the LBB conditions. So I won't go into the mathematical details. So if you are interested, you can look at the paper by both from Professor Betsy's group and from Professor Babushka's group. They individually divided, and there's some small difference. Here, I won't able to give you that much detail without going into detail about how they analyzing the problem. But I can also post some other literature. I find it useful. It could be more on the mathematical side. But what I want to convey in that short lecture is that I want to give you the general idea. So if you're interested, you can actually go deeper in the functional analysis or numerical analysis to understanding it. Okay, but I hope at least I outline that a compete will be necessary. Okay, so the inf-sup condition is very powerful. It actually applies to anything that you need a Lagrange multiplier. It almost always guaranteed to have an inf-sup settle point problem in very high dimensions. It's also crucial for the pole mechanics problem. You can always guarantee that you lead to inf-sup geometry, and you actually need to find the unique point of settle point, which require a different technique than you just want to find a minimizer. Okay, so so let's spend more time. Okay, so I would rather teach a little bit less, but cover that inf-sup. If you actually, let me put it the other way. So the course of computational pole mechanics contain many different problems, but at the minimum, what is necessary is you understand the mixture theory, how to derive the consolidation problem in two-phase problem that are with a deformable porous media, and from the mathematical side, know how to formulate the mixed finite element. Okay, so there's like two small course combined. You can also open a course just for mixed finite element, but that would be but then we will have two students that are interested in mixed finite element. So the populating that, we have the two. And of course, there are more variations we want to cover for the rest of the course, like multi-phase flow. Okay, how do we deal with the thing where we have retention curve with air or other thing, or material that are freezing or whatever, or dynamic problem where we want to propagating a wave, which also would be of interest. But I think from the mathematical side, knowing the inf-sup is crucial for formulating the stable mixed finite element. Okay, if you don't do anything, maybe you can solve the problem, but you cannot reliably solve the problem. In fact, if you use the equal order finite element and you use a very big time step, sometimes you don't have any problem. Okay, but then your solution would not be robust. Okay, and also for the norm, I forget to mention. So what we show you is the L2 norm. Actually rely on the point-wise values. Okay, you can play around with the L. Okay, but a lot of time in finite element, we are not actually interested in that space. We are interested in things that are differentiable, and that would actually require Hilbert space, and then correspondingly there's a Hilbert there's a norm associated with the Hilbert space that require derivative. Okay, so we talk a little bit about that, but this is also another technique to get by the inf-sup is to analyzing it, generalizing it, or think about how to use more smooth functions to get rid of the oscillations. Okay, so I can show you also some example of the instability. Basically, you see a checkerboard pattern, or you see a funny pattern that are just not physical. And I think in the early literature, people confused and think there's a physical phenomenon and try to explain it, and they don't find that as numerics. So okay. So anyway, so I think I just want to stop here, and then I'll try to. I'll actually try to securing the room on Friday. So as you know, this is probably the most difficult thing for the course is to find the room on Friday. Can you go confirm again whether Friday will be available for you?